All right, hi. My name is Brandon. I'm from IBM Research from the Container Cloud team. And I'm going to present to you something that we are working on. We call Nabla containers. So this is the Nabla containers logo. If you're wondering, the reason we chose this is because it kind of resembles the architecture that you see later. So the conventional wisdom today is that people don't believe containers are secure. You know, they would run multi-tenancy with virtual machines, but they don't want to do the same with containers, right? So at research, we thought about this a little bit, and we wanted to dive a little deeper to say, you know, why do people have this mindset about containers versus VMs, right? So how exactly do we want to define isolation? Compare this metric against both VMs and containers, and after we figure out why, what makes people think makes workloads isolated, figure out how to have this isolation be put into containers as well. So I'm going to go through just a really quick introduction to what our threat model is for isolation, and then I'll go through a short demo about our open source runtime, RunNC, that runs Nabla containers. All right. So how we define isolation is that a workload should not be able to access the data or secrets of a co-located workload or container on the same host, right? So a quick example is we have service A over here, and service A has a secret or some data, and an attacker that runs another container on the same host should not be able to access that secret, right? So why is this important? So for us, one of the use cases is, for example, you know, if I have service A over here that has gone through VA checks, has gone through a lot of audit, it's a really secure service, but I have a legacy, like 30-year-old application that has tons of vulnerabilities. An attacker may do a horizontal attack on the same host. So what is container isolation right now? So containers are namespace processes, right? So namespacing is good because by definition it means that the data of one container should not be able to be retrieved from another process, right? But because containers are namespace processes, this means that they are also processes. And so any vulnerabilities or exploits that apply to regular Linux processes would most likely apply to containers as well. So the real main threat that we are trying to address here is this, what we call the horizontal attack profile, which is two containers on the same host going through an attack through the shared privilege component, which is the kernel in our case. So to see what we're up against, let's take a look at a really brief exploit sketch. So this was Dirty Cow Cve that was in 2016. Was quite a popular one. And so what happened was basically this exploit revolved around a race condition in one of the systems. And so what it did was it basically nmapped the page, created a thread that kept running madvisors, and they had another thread that read and write and wrote out of the proc file system, right? And what they're trying to do is exercising multiple functions to trigger the race condition. So to understand how we are measuring isolation, let's take a deeper view of what the kernel looks like. So the kernel to us is just a bunch of functions, right? Kernel is just code. And so how we are modeling it is that what we saw the exploit doing was it was exercising system calls to exercise the kernel code within the kernel, right? So in this case, we have the application on top. So everything outside the green box is user space. And we have the system call, which is the interface into the kernel. And how we're modeling this is every box we have over here, you can think about it as a kernel function. And we can think about, out of all the kernel functions within the kernel, there would be some functions that may have vulnerabilities. And we mark these as the red boxes, right? So the hypothesis that we went with is that if we restrict the top level amount of syscalls that interface into the kernel, we can restrict the number of kernel functions reachable. And hopefully we prevent some of the red boxes from being reachable. So we have less vulnerabilities and therefore potentially less exploits. So great. So this has been done, right? Everyone knows seccomp. So Docker has a default seccomp policy. I believe it blocks at least 44 of the syscalls. And what this is doing is it's doing exactly what we're thinking of, right? What it's doing is preventing access to certain kernel functions. So if we kind of treat the boxes that are grayed out as kernel functions that are no longer reachable, we can kind of see this as, they are basically removed from the kernel itself. So the issue with seccomp policies is it's often difficult to create a generic seccomp policy but still be and be secure. So this is one of the problems. There's another approach of this, which has been syscall profiling. So this is done by several companies like Ocr, Twistlock. And what they're doing is they're running a bunch of tests or running the container multiple times to find the seccomp profile that they can use. So our approach is something called Nabla. So what we are providing is a deterministic and generic seccomp policy for applications that limits to only 7 system calls. And how we're doing this is with library OS techniques. So the general gist of it is that we are taking a lot of the functionality in the kernel. So for example, the TCP IP stack, and we are bringing it up into user space. So example of this, which I mentioned, the TCP IP stack, right? In the TCP IP stack, there's a lot of code, but a lot of the code is, implementing sliding windows, implementing, where should my packet go and things like that. You don't have to run this code in the kernel at all. There's no reason to, maybe besides performance reasons. But so the question is, can we lift this up into user space? And that's exactly what we're doing. We're taking the TCP stack, some parts of the file system, and we are bringing it up into a library operating system here. So we can think about this as we're taking all the functionality and we're sticking it in a libc so that all the functions are done within the user space. And only when you have to talk to the kernel, you have to write a packet or something, then we perform a trap. So that's what the 7 syscalls are mainly doing. So the approach here is kind of, we are using this concept for unikernels, and eventually how we see the kernel is going to become like a microkernel. It's going to be smaller and smaller. So we've done this. I mentioned unikernels already. All this is based on things from Runtime and Solo5, which are from the unikernel community. There is a talk on this in the microkernel track. If you can go back in time like an hour and go to the microkernel track, it's there. If not, we have a paper on this. And so the main gist of it is we will take the unikernels, and we had this thing called the Solo5 interface, which looked kind of like a VM interface. And what we were able to do is we were able to run the interface as a process with only 7 syscalls. And what this meant was that first we don't have to use virtualization, we don't have to use VT, and we get a lot of performance increases because we don't have the additional layer. So memory density performance is increased by a lot. So what we've done is the modifications to be able to run this. So we have a runtime called runnc. So what it is an OCI runtime, which is on this level. So it's a replacement for runc. The only difference is that the Nabla binaries are not traditional native binaries, right? They have special requirements. So what we have now is a custom build process because we are statically linking against our library operating system. So right now we have the application and we rebuild it with this library operating system. However, right now everything is statically linked, and we believe that it is possible to eventually decouple that into the dynamic library. So in this way, we may not even have to recompile the binary. All right, I'm going to do a quick demo to show kind of what's inside a Nabla binary as well as running it with Docker. So we have this repository here we call Nabla demo apps, and it contains a bunch of different applications that we have built. So if we take a look at one of them, this one is the Node Express one, right? So we have two Docker files here. One is Dockerfile legacy and one is Dockerfile Nabla. They are to build the two different type of containers. And before we get to building, let's look at what the app is actually like. So it's your standard node.js, very simple application. You have your app.js and your package.json. And basically your standard Node.js application. And if we look at, for example, this is the original Docker file, so how you build a regular container. So pretty straightforward, copy the application files in and do an npm install, right? So now we're going to take a look at what is in the Docker file for a Nabla container. So because we do the rebuilding, there is an additional step. We have the step that we're using a separate binary. So what we have is pretty much the same thing. We are creating the node application, the npm install. But instead, we are using this base image, which is called Nabla node base. And this base image is just a empty image with just the node binary, the Nabla node binary in it, right? So the takeaway from the differences of the Docker file is if you look at the file system as a whole, it's going to be exactly the same, except the binary in the different file systems will be different. So I'm going to just build it really quickly. So what we're going to do next is we're going to look at the syscall interface and how it interfaces with the kernel. So we're going to start with the regular container. So we run a Node Express legacy. Okay. So we're going to get the IP and the PID. And so what we're going to do now is we're going to trace this process, and we're going to do a bunch of calls on this. All right. All right, so after all those calls, we can take a look at what is the seccomp, well, what would be at least the minimum seccomp profile that would be needed for a regular node application, right? So within the past 20 seconds, these are all the system calls that have been made by the node application. So what we are really interested here is not so much the number of syscall, but the length of the list, right? If an attacker is able to compromise the service, he would be able to call these in any way, right? So if we look over here, we have mmap, we have madvise, and we have read and open. So it's pretty much if you exploited a Node.js application like this with the strictest seccomp policy, well, not the strictest, but a reasonable seccomp policy, then you would still be able to perform something like the decal attack. So I'm going to now do this with the Nabla container. All right. So I'm just going to add this additional argument runtime run in C, and I'm going to have node express Nabla. All right. So now it's running the same application, but our initialization code, we're printing a bunch of statements. But basically, you can see like the components here are part of the unikernel ecosystem that we're using. So we're using the Solo 5 interface, and we're having a runtime, which is a NetBSD kernel within it, which is our library operating system. So we're going to do the same thing with the Nabla container. Inspect. All right. All right. And we see that it only used 3 out of the 7 syscalls. Basically, it's just waiting on a socket and reading and writing packets whenever it has to. Right? All that TCP stack, everything else is all done in the user space. All right, so just really quickly, what we saw is where the asterisk places. So what we saw was the syscall interface going into the kernel. And so the graph on the left actually shows a comparison with regular Docker containers in red, and the blue ones are Nabla. So we ran this for Node Express, Redis, and Python Tornado. And so that's kind of like a really high-level view on it. What we did was we went a little deeper. So what we did was we were measuring the actual kernel functions using the ftrace utility. And what we saw was a similar trend. So the second graph over here on the right actually shows the difference in the ftrace measurements. So I'm just going to touch on this really quick, and so we can get to questions. So something we noticed when we were running experiments is for certain measurements, we saw that Nabla was actually doing a little better than some virtualization technologies. And so we asked ourselves this question, like, what have we achieved something here? And so we wrote a paper about this. I won't go too much detail into this because it's a talk on its own, but you can read the paper. Basically, the contribution that we are making over here is that really you're gaining isolation from the interface, the width of the interface and the implementation of what's underneath, rather than using virtual VT itself. So we kind of said that these are two different ideas and they can be separated instead of coupled together all the time. So this is still a fairly new project, and we have multiple projects that's run NC, which is actual OCI runtime itself. We have Nabla demo apps, where you can do like new different applications, different languages, and all that. And there's also runtime and Solo 5, which is really the meat of the unikernel work. Yeah. So we also want to get some feedback on like what other people think about the metric. You know, are there any other ideas about how do we measure isolation? You know, this obviously isn't the one the one way to measure isolation, because you have things like spectrum meltdown. These are not accounted for in the metric, so there's still a lot of exploration there we have to do. All right. If not, this is the end of my talk. Thank you very much.
Thanks for the talk. Can you comment on the different approach with regards to gvisor from Google?
Yes. So we actually wrote a blog post about this. But I'm just going to show you a picture just to kind of, okay. So the approach that gvisor takes is kind of, wait, let's see, that's a side-by-side picture, okay. Right. So this picture kind of summarizes gvisor and Nabla side by side. So gvisor takes, part of the gvisor philosophy is that there is a level of guarding between the process itself and the library OS, and you have another level of guarding between the library OS and the kernel itself. Right? In the Nabla approach, what we're saying is the process and the library operating system are currently coupled together as one, and what we focus on is really securing this interface. There's nothing to say that we can't do what gvisor is doing, but our main focus is basically making this interface as small as possible. We have measurements on the gvisor stuff also that I can show, but I think you can see that from the slides. I think it's a lot clearer. Yeah. And yeah, feel free to look at this blog. It's a Nabla containers blog. We have a bunch of information about the gvisor stuff as well as the kata containers analysis.
Any other questions?
In order to remove the necessity to rebuild the binaries, would injecting the library using LD preload and removing the standard C library, would it kind of work whilst you still have the syscall filtering?
So the library was dynamically loaded. I think you could do it as long as you have control over the first like the loader at least. If you had the loader and then you basically hijack the start command, I think that would be okay. So there's also another thing, which is currently our library operating system uses a NetBSD library operating system. So for Linux compatibility, either we need an additional layer that does translation, or we need to use something like LKL, which is a Linux library operating system. But like what you said, once you have it as a dynamic library, I think LD preload is pretty much, we can do that. Yeah.
Actually, I can answer this question because I was contributing to a project that does exactly that. Modifying library calls using LD preload. The project is Scratchbox 2 that is used by Mer project and Sailfish OS to build, emulate cross-compiling by making that it's not making impression for the process that it's not cross-compiling. But the problem with this approach is that it's very fragile. If you have glibc, it has tons of library functions, and you need to replace all of them because it doesn't have a system call interface in separate library. So if you replace open, for example, you have to replace fopen,
Yeah.
popen, and stuff like that. So it leads to very fragile. So Scratchbox 2 works, but there are still many different problems with this approach. If we had system calls separated in a separate library from glibc, it would be much simpler, but it's not the case.
Yeah, so we actually, we did an experiment where we only wanted to move the TCP IP stack. And that gave us problems because that depended on a different part of the kernel, and then now we had to expose more things, right? So I think that's kind of similar to the issue you're talking about. For our case, what we're doing is we are forcing our libc onto the application. So in that sense, we are assuming that all system calls go through our library operating system. So in that case, it's a bit more relaxed for us. Yeah. I think we had one question. Yeah.
So are these Nabla binaries special type of binary? Can we only run them inside these containers with your runtime, or can we like run it on the host OS for some debugging or whatever purposes?
Right now it runs on, so there's this part of, so okay, let me just show you a picture. So this is actually what the Nabla binary looks like in the middle. So this is thing called Solo5, which is an interface that originally was for unikernels. Well, it still is. And what they have below that is the tenants. So this can run on multiple things. And so Solo5 actually has multiple options for the backend tenders. So you can run this on KVM as well. Yeah. So you can also run this as like unikernels as a service on VMs.
Hi, thanks for your talk. I have a question. How do you like avoid calling mmap if applications requesting memory? So
right now, so the interface is very VM-like. So right now, what happens is when we allocate. So in runc, we get the memory requirement. Runnc, we get the memory requirement, and basically we say, okay, we're going to create a unikernel with this much space. So we give the chunk of memory to the unikernel, and it does its own memory allocation within itself. So there is still we kind of take advantage of the idea that it's going like if you specify a big amount of memory, it's not going to be used. It's going to overcommit anyway. Yeah.
Time for one more question. No, that's it.
Thank you.
Thanks.